Good afternoon. We're here for another session of geometric ellipse formula derivation. And that is what I'm doing today because that is the idea that was on my mind when I went to sleep and when I woke up this morning, turning over formulas that I could use to integrate the volume for a elliptical cylinder into the equation, into the derivation process. So what I have determined is that the surface area formula is the problem because it has not been developed with known factors. The factor h and p, the height of the cylinder and the perimeter of the ellipse, are both undetermined, and we try to develop an equation for the surface area under these conditions. So what we have is an approximation for the surface area. And if we were to have a better approximation of the surface area, or even an exact formula for the surface area, we would get exact ellipse perimeter values. So what we know is that the first term is correct in our surface area formula, 2 pi AB. However, the second term, 1 plus 2 pi k, is not fully correct because the second term of that set of values, 2 pi k, is not exact. It is not what would actually occur if we knew a formula for the perimeter of the ellipse. So I have a k in here because I want to try a new experiment and determine the factor k that I'm just sticking in there next to 2 pi and see if there is a number that I can use that will correct the formula. So we are starting on a path of trying to correct the surface area determination formula. So we have h equals 2 pi AB times 1 plus 2 pi k minus 2 pi AB. And that is how we would use the surface area approximation to find the height of the cylinder and consequently the perimeter of the ellipse. That's this formula here. Now, we're going to work this formula and try to find the value k in this formula that would be the correction that we would need to add in order to make the formula more accurate, if there is such a value, and it is a single scalar number. So we found out h squared after we combine like terms, and we solve for k. H squared is equal to 2 pi squared times ABK. That's pretty simple. Looks like if k was a real number, a real factor to correct it, our work would be simple and easy. So let's solve for k. K equals h squared divided by 4 pi squared a times b. And now we're going to test some k values using known a and b values. So plug a and b into the formula, we come out with a k, and And we also have a known h. H would be the perimeter of ellipses from a table, from a calculator, online calculator, that would give us these perimeters, and we would use h to be equal to the perimeter as the model was derived in the beginning. Let's see what came out in this table. Now it's time to go over the table of k values. So if you're a systems thinker, you will realize that even in the number system, you have just that, systems and subsystems. And so this formula that I've been working on has some systematic behavior that is being discovered. So we're going to analyze it in the sense of analyzing a subsystem of the number system. We have 4 columns that are populated at the top of the table: the semi-major axis, the semi-minor axis, the perimeter, and our fudge factor k. The purpose of k is to show what number would need to multiply the second factor in the parentheses in order to give us correct output. It is the correction needed for the formula that I derived. So we have the semi-major axis at 5, the semi-minor axis at 3. We would get a perimeter of 25.527, and to make that formula correct, k would need to be 1.100. A equals 9, b equals 6, the perimeter 47.596. To make that formula correct, we would need 1.063. A is 10 and b is 5. The perimeter would be 48.442, and the correction needed would be 1.188. If A is 12, B is 4, perimeter is 53.458. We would need a correction factor of 1.508. A is 50, B is 25. The perimeter of that ellipse, according to Ramanujan's first approximation, by the way, this whole perimeter column is computed by Ramanujan's first approximation formula. So perimeter 242.210, and k would need to be 1.188. Notice that that number occurred earlier, and it always happens that when the semi-major axis is double the semi-minor axis, the correction factor needed would be 1.188. Happens here 10 and 5, happens here again at 50 and 25, 1.88. It happens every time. That is one of the systematic behaviors that we would want to try to discover what the cause is. So A is 50, B is 35. The perimeter is 69.118. And to make the formula correct, k would need to be 1.048. A is 12, B is 3. The perimeter of that ellipse is 51.465. To make the formula correct, we would need a k of 1.864. Here we come with the double A. A is 6, B is 3. 29.065 is the perimeter of that ellipse. And once again, when we have A double to B, k would need to be 1.188. And I continue to do some doubles just to show you that that happens every time. A equals 12, B equals 6. that ellipse will have a perimeter of 1.131, and to correct it, 1.188 would be needed for K. And finally, the most obvious one, A is 2 and B is 1. That ellipse will have a perimeter of 9.688, and to correct it, K would need to be 1.188. So I verified that behavior where A is twice the value of B, then we would get the same value of K in all those instances. So next, I wanted to see what happened when we kept A at one of those double B values, 2B, when A equals 2B, and we varied B. So this is what happened. A has the value of 10, B the value of 5, and we get the perimeter of the ellipse from Ramanujan's first approximation of 48.442, and as expected, K needs to be 1.188. That is very consistent. But now we're going to keep A at 10, but B is decreased by 1. And the ellipse perimeter falls to 46.025, while K goes down as well, up as 1.341. My bad, it goes up. Then when A is 10 and B is 6, that means we have increased B from 5 to 6 compared to this value. K has gone down to 1.100. So it appears that when B decreases, K would need to increase, and when B increases, K would tend to decrease. So they are inversely proportional. And I expected the same thing to happen if we kept B constant and varied A, but that is not what turned out to be the case. You see, this systematic behavior of this formula is dependent upon the perimeter and the formula K. So what happens to K depends on the perimeter, and the perimeter is a non-linear function of A and B. And it turns out if we vary the semi-minor axis, which is always smaller, then we get inversely proportional behavior. But if we vary the major axis, we are going to see that it is directly proportional. So we went from A equals 10 to A equals 9, and 5 was unchanged from this test case here. So 9 and 5 now. And it turns out, well, the ellipse did get smaller when A got smaller. It's directly proportional, but by a much larger amount than it would than when B was reduced. And instead of increasing as we expected with A to do if it was following B's behavior, decreased when A decreased. So the relationship is directly proportional, and that is because it goes through two equations to get to K instead of one. You have to go through the perimeter, Ramanujan's first approximation formula, and then A also has to go through the K formula in order to produce a behavior. And it turns out that when A, which is a much larger influence on the value of the perimeter of the ellipse is computed when A is changed, then the ellipse gets smaller by a larger amount because it is the perimeter squared, and it has A as being a much larger number has a much larger effect on the perimeter, and so it is not inversely proportional because of that. It is directly proportional. So these are some nonlinear behaviors that we're looking at here. And with nonlinear systems, things just do not always turn out the way you expect from first glance. You have to look deeply into the behavior, and that is what we're doing. This is a system analysis of a number system. So A is now increased from 10 to 11, while B remains at 5, so we didn't change B. And once again, we got directly proportional behavior. The value of K went up instead of down as it did when we varied B, the semi-minor axis. So that is a lesson. Always be careful when you're dealing with nonlinear systems where you have terms that are squared, and when you have a system of equations, because things may not happen from the first input to the final output as you would expect. When we vary the semi-minor axis, it had us expecting one type of behavior, but when we varied the semi-major axis, we found out that another type of behavior came out, just the opposite of what happened with the semi-minor axis. That is system analysis telling us the truth. Now, we're going to do it again. I say, well, once it's not enough, let's try it with a double 6 and a single 3. So 6 and 3 are double relationship. A is twice B. 3 times 2 is 6. And when we did that, we got 1.188. That is the behavior that we have found to be consistent. But now we're going to keep 6 constant. It's the semi-major axis is going to be constant. Semi-minor axis will be decreased by 1. And it's inversely proportional because K went from 1.18 to 1.508, so that's an increase. Semi-minor axis decrease, K increase. Okay, we're going to do it again. 6 is constant, but this time we're going to increase the semi-minor axis, B. And when that happened, the semi-minor axis went up, K decrease, inversely proportional. But now we're going to keep 3 constant. Semi-minor axis is constant. Semi-major axis is going to decrease by 1. And here we have that the output K also decreased. And so it's directly proportional. And once again, we increase the semi-major axis A from 6 to 7, keeping the semi-minor axis constant at 3, and K increased to 1.289. So it's directly proportional. So when we vary A, we get directly proportional behavior. When we vary B, we get inversely proportional behavior. And it took me a number of passes through this table to discover that. The first time I discovered that the inversely proportional behavior of B, and I said, well, that's it. They're all going to do that. And I found myself starting over again. Now, here's something. When A, the semi-major axis, and B, the semi-minor axis, are equal, we get 6.2831, which happens to be 2 pi, somewhere thereabout. So the circular behavior of the formula still persists, even though we, in its derivation, try to convert it into an elliptical formula. And even though it has some elliptical behavior, it was not a complete conversion, as we see is necessary to have a correction factor k in there to make it behave exactly as an ellipse should behave. But we don't have to make any corrections to make it behave exactly as a circle should behave, because k equals 1 when A and B are equal. In other words, we're dealing with a circle, and the perimeter of a circle of 1 is 6.2832. So we began the model as a circle, and it falls back to a circle when the axes are equal, and that is good behavior. That is expected. That means the formula reduces to the proper case. So the next experiment involved keeping the semi-minor axis equal to 1 and increasing the semi-major axis one step at a time from 1 to 10. And we've seen the 1 case, but then we're going to go 2, 3, 4, 5, 6, 7, 8, 9, and 10. Find out what behavior comes from K, what behavior we get from the perimeter, and over here in these columns we have a difference table. A difference table from K, a difference table of the differences, and a difference table of the difference of the differences. So we took it 3 levels of differences, and sometimes if you're good at analyzing difference tables, you can discover some things, but we're not going to go into that in this analysis, just the first column to find out whether K increases as the semi-major axis increases. And yes, we have that directly proportional behavior. 2, K goes up, raise it again, 3, K increases again, 4, K increases again, 5, K. So the correction has to be larger as the semi-major axis increases. So remember that K is a correction factor. And when we get to 10, we would need a correction factor as large as 4.176 to make my estimate, my formula work, the geometric formula I called it. Now, you see that the value of the increase is pretty close, except in the first case when it's twice, it only gets 1.188, but then as it increases 3 times, it's 3.19, 4 times 0.355, 5 times 3.71, when A is 6 times B, 0.384. K increases by smaller and smaller amounts as the semi-major axis. So I don't know where that's leading, but the limit is going to be in that sequence. But we could probably figure that out, but it's not important. We just wanted to show something about system analysis, and that this formula is a subsystem of the number system and what type of behaviors, what type of things it's going to do. Then we did the opposite of that. We kept 10 constant, and that's the semi-major axis. And we're going to increase the semi-minor axis starting from 1 and increasing up to 10. And what happens? Well, in 10 and 1 we get 0.393, but then it decreases. So whenever b, the semi-minor axis, increases, the value of k decreases by smaller and smaller amounts still, though. And that is the behavior that we discovered earlier, but it is systematic. So this behavior could be pinned down and analyzed to tell exactly what the cause of all these movements in the numbers are, if that was very, very important. It is important to get an exact formula of the ellipse, but I'm thinking that this geometric formula, this first pass on it, might not be the end of the line. So we may be able to get a better formula. We spend more time on doing that. But once again, you see the circular behavior. A equals B. We have a circle, 6, and K would not change anything. It would be the value of 1. So in the limiting case, where A equals B, the formula reduces back to this formula for the perimeter of the circle. So at least we succeeded at that part, but we haven't been able to figure out how to make it give us the perimeter of an ellipse every time. So we want a formula that every time we compute a perimeter, we would get a 1 for k. 1, 1, 1, 1, 1. Or we wouldn't need any fudge factor. That would mean success. No correction necessary. And with that, we will say that we have found some very interesting things in this formula to keep us happy and active. So there we have it again, another step in our journey to derive a formula for the perimeter of an ellipse. It might be a little better than what we have now. If we can get an exact formula, we can feel safe with playing around with asteroids in space and whatever other things we want to do in space, because ellipses are out there. And if we don't understand them, well, we could make a mistake. But right now we don't have anything to worry about, because we got a pretty good formula with Ramanujan's formula and the elliptical integral of the second kind. They're doing well for now. But thank you for listening to this continuation of the work on elliptical perimeters.